Oh, another type then. This is back in the realms of things that were once tried and no longer used, is the optical pressure sensor. This is another thing that somebody tried. They had a great idea. They actually built these things. No more. No more. We don't see these anymore. Hopefully. If you have a closed tank, you need to know the pressure at the top of the tank as well as the pressure at the bottom of the tank. Because if it's a closed tank, you haven't got atmospheric at the top. So you need to know what you're comparing with. So if you have a closed tank, you measure the pressure at the bottom and you measure the pressure at the top. And the pressure caused by the height of liquid is the difference between the two. Now, what I might do, I might just give you an example of where this is used. If we are making paper, we have a machine called a head box. It's called a head box because it provides a head of pressure. Inside the head box, we have to maintain a certain level of liquid, which is called the liquid level. And that level of liquid has to be maintained at a certain size. On mine, I'm going to say that's 200 millimeters. I always have to maintain 200 millimeters of liquid. Now, in order to maintain a steady jet of paper pulp coming out here, I actually need about 400 millimeters of H2O pressure. In the top here, I have an area which is called the air pad. And I've got a machine, a compressor, which can blow compressed air into that air pad. So, hopefully you can all see that if I need 400 millimeters of pressure at what's called the slice, and I've only got 200 millimeters of pressure from the liquid level, I have to have 200 millimeters of pressure in the air pad to get my correct pressure. Now, if you could just give me a smiley face if you're happy with that. Okay, now the way this all breaks down is we have a pressure sensor at the bottom and we have a pressure sensor at the top. And the pressure sensor at the bottom is reading a thing called the total, oops, oh dear, try that again, the total head. The pressure sensor at the top is reading the air pad. So I know I need to maintain, my criteria is I need a total head of 400 millimeters in order to maintain the jet coming out of the head box. I know I also have to maintain 200 millimeters of liquid level. And so what I say is, well, the liquid level is the total head minus the air pad. So liquid level equals total head minus air pad. So I can get all of those readings if I have a sensor at the bottom and a sensor at the top. Right, different ranges of gauges. Strain gauges are good for just about everything. Capacitive sensors, they're also good for almost every pressure. Piezoelectric, particularly good for high pressures. We haven't got piezoresistive on there, but they're good for very high pressures. In fact, they're better for high pressures. Nowadays, Have I got this on a slide? Okay. Nowadays, there are basically 3 types of pressure sensor. Or 4 if you count the strain gauge. There's 4 types of pressure sensor. There's ceramic capacitance, piezoresistive, and piezoelectric. There are still inductance pressure sensors out there. Just throw them away. Nowadays you buy a ceramic capacitive, or if you don't want to buy a ceramic capacitive, you buy a piezoresistive or a piezoelectric. Piezoelectric has got a high gain, not good for absolute, but absolutely brilliant for vibration. Piezoresistive is not as accurate, and it gets badly affected by vibration. So your first choice is always got to be your ceramic. And really, in this day and age, even in WA, we should be throwing the other stuff away. Sometimes, with pumps, especially if I'm on the outlet of a pump, I'm on the outlet side of a pump, we've got a pressure gauge. Now, as each blade of that pump goes round, that pressure gauge goes up and down because it's picking up the pulsations. That pressure gauge will very soon be completely stuffed. So what we do is we put in a thing called a snubber. The name comes from a piece of rubber that people put on anchor lines. This thing here is a piece of rubber that you put on an anchor line. It's called a snubber. And the idea of it is, as the ship moves with the waves, it stops the line cracking, because the line will crack and go and straighten, and after a while the line will part. So a snubber on an anchor line stops the sudden cracking. A snubber on a pressure sensor stops the pulsations. It's just a piece of pipe with a small hole in it. Other ways of stopping the pulsation is to fill the gauge with stuff. If you fill the gauge with oil, that will stop it pulsating so much. If you fill it with silicon, that's even better, because silicon is what's called a non-Newtonian liquid. And what's special about silicon is when you stir silicon, it gets thicker. It's a bit like a thick shake. So if you stir silicon up, it thickens up. So if there are lots of pulsations, silicon will just thicken up and it will kill the pulsations. Was there anything else I was going to... What was I going to... come back. Here's a conversion. When we measure pressure in lots of different ways. There's lots of different ways we measure pressure. Sometimes we measure pressure in kPa. Sometimes we measure pressure in equivalent millimeters of water or millimeters of mercury. What that means is, if I've got a piece of, let me grab my pen. If I've got a piece of pipe and I've got a liquid level in that pipe because I'm blowing in one side, the pressure in millimeters of water would be the amount that I move the water level. See, this is all full of water in here. So if I move that water level by, I don't know, 20 millimeters, then I would say that the pressure I'm exerting is 20 millimeters of water. Similarly, if I had a piece of tube and this time it was filled with mercury, and I'm pressing down, I'm pushing in that bit, I'm blowing in there, then I would say if that mercury was moved up and down by 5 millimeters, I'd say that the pressure there was 5 millimeters of mercury. Hg is mercury. Right. Densities. Densities, different substances with different densities exert different pressures when there's an amount of them on top of something. Mercury is much denser than water. So, for instance, atmospheric pressure, if I did the thing with the pot that I did at the beginning, so I've got a pot in there, I would be able to draw that up approximately 10 meters before I created a vacuum. But with mercury, that's very much less. I'm trying to remember what it is. I think it's 360 millimeters, but I can't be exactly sure. Almost certain it's 36 centimeters. With mercury, I would be able to draw that up 36 centimeters before I create a vacuum in top. And the reason for that is because mercury is so much denser than air. Here I've got a little question I'm asking. If I have a submarine visiting the Titanic, and it's in seawater, and seawater has a density of 1025 kilograms per cubic meter, what would be the pressure on the window? So what I'll do is I'll just do that. We'll do it together. Let's have a look. Depth is 3810. So if you remember, the equation is P equals rho G H. Now, pressure is what I'm trying to find. Density is 1025 kilograms per cubic meter. G is 9.81 meters per second squared, and H is 3810 meters times 3810 meters. Now, if somebody could possibly grab a calculator and do that for me, I'd be very pleased. I'll just see if I can grab my calculator. So
38.3 times 10 to the power of 6.
Oh, thank you very much. P equals 38.3 times 10 to the power of 6 pascals, or 38.3 megapascals. That's a lot of pressure. Now, the next question, just going back to the next question, is that if we have a window that has a surface area of 0.1 of a square meter, what is the force on that window? So, let's get another window up. P equals 38.3 megapascals. Force equals pressure times area equals 38.3 times 10 to the 6 pascals times 0.1 meter squared. So that equals 3.83 times 10 to the 6 newtons equals 3.83 mega newtons. Now, those of you that remember right at the beginning of the course know that personally I have absolutely no idea what a newton is. But I've invented my own unit of force, which I call the fitter. And the fitter, oops, let me get that a bit smaller. 1 fitter equals 1 kilonewton. So if 1 fitter equals 1 kilonewton, we're talking in terms of what? 3,000, nearly 4,000 fitters standing on top of my piece of glass. Now 4,000 fitters, a fitter being quite a big bloke, 4,000 fitters is a hell of a lot of pressure in it. I think you'll all agree. That's why I prefer using fitters than newtons, because I understand how big a fitter is and I don't understand how big a newton is. So I've got 4,000 odd fitters on top of my piece of glass. It's no wonder that people in submarines get a bit nervous. Okay.